webinar. So today we have Darren Crannis from ECA's technical team who'll be presenting to you on RCDs and SPDs. So Darren will be presenting to you for the first part of the session, and at the end we'll have a short amount of time for your questions. So please pop these into the Q&A box. By attending this webinar, you can claim an ECA Professional Development Certificate by filling in the form, which we'll share at the end of the session. And this session is being recorded and will be available to rewatch on the ECA website. So thank you for joining us, and over to you, Darren.
Good afternoon, everybody. I hope you're really well and stay hydrated. Thanks for joining us for this lunchtime as Technical Tuesday. And today we're going to go over sort of understanding RCDs and SPDs, including common myth busting. So what do you get from the ECA before we start? Well, not only hopefully do you enjoy these Technical Tuesdays, but we're also a wraparound service for the whole business. So I'd like to think that we offer great technical advice and technical support for our members, but certainly it doesn't stop there. That we're there to facilitate the whole business, including sort of expert legal and business support, HR support. We have some great packages as in the ECA risk assessment, ERAMs, and eComs, especially useful for your annual assessment and your compliance of your personnels. A really good package that's really heavily utilised now, especially with new standards coming out this year. 5839 Part 1 was one of them, so the fire detection standard, our BSI library. And I think that's about £100 a year for about 90 standards, all relevant to the electrical technical industry. Not only that, we give you some great representation and lobbying, and also the sort of CPD events and networking, which I'm sure you're familiar with in your region. So let's crack on with this today. We're going to go over sort of more in-depth understanding of RCDs. We're then going to sort of transfer that into SPDs, surge protection devices. We're going to display the CPD QR code, as Kat has mentioned. If we've got time, and we might be pushed for time today, we'll go on to Q&A. You're welcome to stay as long as you want. We can get through some of those Q&As. Any Q&A we don't go through today or answer today online, if you put it in the Q&A chat, we will respond to that after this in the next few days. So bear with us if we don't answer your question today. My name is Darren Crannis. I'm a technical manager here at the ECA. I've been with ECA now for quite a few years, coming from a contracting background, predominantly in sort of heavy industry and electrical inspection and testing. What's great about every member of our technical team is we all sit on the national committee, so the national standards. So what you hear today and what we sort of hear through our guidance and when we present or when we come and see you, is you sort of get it from the horse's mouth, as it was. Because we sit on those national committees, we can give you sort of that detailed opinion of what we, and it's really useful for things like what we're going to go through today. So without further ado, let's crack on with RCDs. So we're going to go through a little introduction on these, the roles and principles of RCDs. Things have changed, especially in the last sort of 5 to 10 years. The selection, up to sort of a couple of years ago, there was only really 1 or 2 types of RCD. There are many today. We'll go through some good installation practices, especially with sort of net zero challenges on this. We'll talk a little bit about inspection testing. We'll save the Q&A from that to the end. Earth leakage protection, which RCDs predominantly look after now, isn't a new thing. It's been about since the 1930s. RCDs have been around for a while, and they've really evolved in the last 10 years. We have many new types doing many new things, some of which we may not even mention today. It can be confusing, it can be expensive, and it's important as designers that we get this right. We're mostly focused today on Amendment 3, so BSM 671 Amendment 3. That's the Brown Book, which was Amendment 2, with the free bolt-on. And that's the current standard that we're using today. And if you aren't working to Amendment 3, that bolt-on's a free download, so you really should be working to that. RCDs aren't just for socket outlets and cables and walls. They offer protection against the following. So indirect contact, we now call that fault protection. Supplementary protection against direct contact, so we call that basic protection. Protect against fires and thermal effects. So often the sort of 300 milliamp was a thing, sort of wooden buildings and barns, and insurance companies may have specified these for effects against fire. Additional protection. We're all used to those 30 milliamp RCDs for additional protection. They came in many different products. We can buy these as devices. We can buy them in products. They're commonly used in special locations, or they're integrated into products themselves. And we'll go over sort of the implications of when they're built into products as well. How do they work? They are very, very simple devices. Years ago, they were the old voltage operated trips. You may see those with a big yellow button on, hardly ever worked. They were around in sort of the late 70s, very early 80s, really a thing of the past. And most of the time, they weren't even wired correctly either. So they sort of offered minimal protection, if any. We moved away from voltage operated to current operated. And they're really simple in how they work. All they do is they look for an imbalance through a coil of what goes in must come out. So it's the same as sort of counting things sort of in and out of a place, a nightclub. They're counting you in, counting you out. They've got to tally. And what happens is it's a very sensitive little current transformer. And if there is an imbalance, and that could be 30 milliamp, it could be 100, it could be 300, it will trigger a relay to open up the contacts on that device, whether that's an RCD, an RCCB, or an earth leakage circuit breaker. It will actually disconnect the circuit. Now, the real difficulties come of late with RCDs is where we hear about this blinding effect. And if you look on the image at the moment, kindly given us by Beamer, you'll see this coil, this round ferrous coil. And this sort of DC phenomenon we're on about, and that blinding, is all about that coil being saturated with the effects of the DC. And that affects the ability for that tripping coil to work. So when we talk about DC blinding, it's that little tiny coil, and it just becomes stunned. It becomes magnetized in one way, and it's unable to detect that imbalance. And there are different sort of levels that RCDs can handle with this, sort of from the type AC, which is virtually nothing, up to sort of type A's, B's, F's. They have a sort of more tolerance in that window. But that's essentially how an RCD works. With 30 milliamp RCDs, it's actually detecting at the 50 volt equivalent. And as you know, the 50 volts sort of across the heart is enough to stop your heart. So the 30 milliamp does come from that 50 volts calculation. Looking at indirect contact, for those who are old enough, or fault protection, as we refer to it today. And this is the key point of this. It's where disconnection times or your ZS values cannot be reached, and often they're exceeded. So we use the RCD for fault protection. We've been doing this for years with TT systems, where there's an earth electrode and it's a high impedance value. So therefore, we tend to put that 100, 300 milliamp time delayed RCD at the front of our installation. We can do that with TN systems. So where low impedance values cannot be achieved, or there's some doubt in their stability, again, that's looking at TT, but can be applied to TN. There's an alternative method. And this time, an RCD is a practical solution because it allows us to go beyond those ZS values. Because the important protection by the RCD is it's not exceeding that 50 volts. And it's that 50 volt rise in potential that can cause harm to humans and livestock. And anything over 50 volts will disconnect. And that's that 30 milliamp value. So it's important that when we have, for example, commercial installations where maybe the boards are at far ends of the building, with tucked away in risers, you might have long ring final circuits, long radial circuits, long lighting circuits. You can use RCD as fault protection. And you've got the values here, which is kindly given to us by Beamer in this table. So you've got your 16670 value for 30 milliamp RCD. And they're absolutely brilliant in this situation where you just, should we say, need to go beyond those ZS values. How many different types of RCD have we got? Well, RCD, or residual current device, is just a generic term which encompasses quite a few devices. So we've got the RCCB. You may see these a lot in split load boards, typically built to BSEN 61008. You might get some of the older variants to BS4293, and they're residual current circuit breaker without overload protection. So that's why special considerations need to be in place if they're in split load boards, or they might be incorporated into industrial outlets like commando sockets, for example. We have the RCBO, which I think we all love. So that's the combined one. That is protection against overload, typically BSEN 61009 sort of series, and that's a residual current circuit breaker, RCBO. As we get to bigger frame sizes, we might be looking at earth leakage circuit breakers at ELCBs. You'll see this typically coupled with MCCBs or ACBs, for example. You may see that on generators. You may see it even on large battery storage. To sort of, that's really offering the full protection. You may also see it built into the charging pins, etc. And then we have the great socket outlets. So 7288, where the RCD element is built in to those socket outlets. It's designed really for ordinary use, so you can put these out and about in offices, in workshops, and it's sort of a self-reset thing. Save someone going back to the board. Can be expensive, but can be flexible, ideal for floor boxes. So the different types of RCD, we highlighted this earlier. Type ACs, we've had them for decades. Great on purely resistive loads. So that might be immersion heaters, or it might be sort of direct sort of panel heaters, linear loads. Really now they are a thing of the past. Type A, with that sort of 6 milliamp sort of I guess threshold, they're a bit more tolerant to sort of DC noise, is common. You might start seeing things where type B are being specified, maybe for solar PV, if that's how you choose to install your cables in walls, and possibly things like heat pumps. When selecting your RCD, it's important that if you've got generating sets, so solar, battery storage, they are all generating sets. We do need to disconnect all the poles, and that also includes the neutral. When it comes through specifying RCDs for equipment, we should take into account the manufacturer's instructions. And we do that in BS 7671 because we're allowing a manufacturer specific really of new innovation products to let us know that there might be some additional information that we may need to safely put that equipment into service. So we do allow innovation in BS 7671, and part of that is allowing the manufacturers at times to guide us, but they are a consideration, and sometimes the considerations may be onerous, that they may not make any engineering sort of logical sense, or there may be other ways to achieve the same level of safety. So that's why we say that manufacturer instructions shall be taken into account. We should confuse the type of RCD with the current time characteristics of the overcurrent device, so circuit breaker or fuse. Especially with circuit breakers, they are also called B, C, and Ds, and we have RCDs that also are called B, F, A, etc. So we've got to make sure that we get these right. I think if we were to go back through the standards many years ago, we probably wouldn't have chosen the letters to be similar. We probably would have chosen a different method. But just be careful when you're choosing RCBOs that you may, for example, pick a type B RCBO as in current trip, but with a type A RCD built into it. So it can be complicated. It could be expensive. So make sure you sort of get those right when you specify, and obviously check them at wholesalers before you install them. As we move up through the selection of RCDs, because there's a unique difference, which we'll come on to later, between the type Bs and the type Fs, they are much more expensive than your type As. And it could be to the tune of a couple of £100, £300 more expensive. So sort of making sure we select the right ones is really important. Question at the moment is around heat pumps. And this comes into our helpline. I know it's been spoken about a lot in industry. And the question is, Do they require additional protection via RCD? And the little cog in the corner means we've got a guidance note for our ECA members on this. You can download that from our website or even through your app. So importantly, heat pumps are covered by their own product standard, and they fall into BSE NIEC 60335-2-40. Quite a mouthful. It's an international standard, so it's written for the whole world. And guidance from the heat pump associations is typically based on domestic installations. That there are some circumstances where a circuit supplying a heat pump may not need RCD. So heat pumps are not a special location by themselves. They're not in the back of the book. They're not a Part 7. So normal BS 7671 rules apply. So if you're on a TT installation, you probably do need RCDs protection because you're extending disconnect. You're sort of going beyond your ZS values. If you've got a long circuit, again, you may need an RCD, and it's important to get the correct type so it works properly. If you're putting the cables in walls, for example, especially domestics who are hiding those cables, then you're going to need to protect those again. But there may be occasions where you're using an armoured cable or a flexi shield cable, and it wouldn't necessarily need an RCD on it because it's an earthed screened cable. So we're back into the BS 7671 thing. However, some manufacturers, and it's not all manufacturers, state in their instructions that it may require a 30 milliamp RCD, or it's advisable to fit a 30 milliamp RCD, and they may give you the type. And in that case, that is something you need to take into consideration. It's still a consideration. However, be aware that if the type of RCD has been specified and you are installing those cables either in wall or even direct on the surface, be aware that manufacturers offer a warranty, and a warranty is a gift from the manufacturer to the end user, and that warranty may be invalid. So if the instructions do ask you to consider or state to put in maybe a type B or variant RCD of 30 milliamp, you need to have a think about that, because it may not fit and that may invalidate the warranty, and you don't want that for your client. So look out for what the instructions fit. Often it's not, and again, it's not all heat pump manufacturers. You might be second or third on site when it comes to this. The sort of mechanical guys may be in first, you may be in second. If you're not left with any instructions, you really need to ask the plumber and mechanical guys, can I have the instructions? Can I look through them? Because it may end up costing you a bit more, and you don't want to leave the client without a warranty, for example. Again, it's specific to each manufacturer. They have different requirements. That was a fitting time really to come on to Amendment 3. We said we'd talk about Amendment 3 today and small changes there. It was always a requirement in BS 7671 to wire things up properly, put them in the right terminals in the right way. But we didn't really make that clear. So the developers of the standard BS 7671, so the JPAL committees decided that they would make this crystal clear for users of the standard. So a new regulation was brought in, and that basically saying that we've got to make sure that the equipment is suitable for the direction of sort of energy flow, power flow. So that is obviously energy now, it can go both ways. So battery storage systems are a classic example. It's importing and exporting all the time. Solar PV, when solar PV inverters first start up, they're actually current using, they're looking at the grid first, and then they're going to go backwards, hopefully, with some good, free, cheap energy. And the worry there actually was if there was a fault and that RCD did disconnect, that there might be some voltage sat on the top terminals and it might damage the RCD. So that's why it's important that we look at the direction of energy when it comes to things like heat pumps, vehicle to grid, solar, and other generation, that we select the right device. And this isn't just BS88 fuses, which are sort of bi-directional. Anyway, this is MCBs, so circuit breakers, RCDs, RCBOs, even MCCBs and ACBs. So it's best that you talk to the manufacturers, depending on the frame size, and find out if they can take energy both ways and what the restrictions are. Because, for example, MCCBs and ACBs may be bi-directional, but can only take fault up to certain fault levels in certain directions. So if you're building panels, consider that. if you're in sort of domestic and commercial installations, just be aware that if you've got energy flow going both ways, you'll need a bi-directional device. And they're very, very common now, and they've come right down in price. I think they're near on the cost of your traditional RCDs, for example. With that, we had a couple of definitions in there, basically telling you that one goes one way and one can go both. Selectivity of RCDs, we do this all the time with good circuit design, with circuit breakers and fuses. We're probably not so good at understanding this for RCDs, but the same applies. So we call this selectivity. We used to call it discrimination up to a few years ago, but it's important that we remember when we design with RCDs. Now, predominantly this might be in TT systems, and it is very achievable. You might see these, especially on sort of EV car parks, for example, that we hit that 3-to-1 ratio, that 300 milliamp, 100 milliamp, 30 milliamp. And we can put time delays on the 300s and the 100s. We shouldn't really put two 30 milliamp RCDs in series. There are additional protection. And the whole thing is actually that if we get a fault sort of right at the end of our circuit, the device closest to that fault will disconnect. Certainly if we're following that 3-to-1 ratio, that will normally happen. There are times actually where sometimes you can't get away with the sort of 30 milliamp RCDs in series. And again, I sort of go back to EV charging on this, where you might have to protect that circuit going out to the EV charger because it's in a wall, and then the EV charger might have an RCD built into it. So you've got sort of two in series. You'll get partial selectivity there. If there is a fault, one or other will disconnect. I wouldn't worry about that too much. That's something that's sort of generally quite hard to achieve in that situation. It's fearful of unwanted tripping. I'd like to think things are getting better on that, but there are things we can do with this. And I think we've been doing that naturally over the years anyway. We've been looking at things like splitting the circuits up. And that does really help as well, about that whole 30 milliamp earth leakage, trying to minimize the effects of excessive earth leakage onto our RCDs. And we can fit things, especially with the time delayed RCDs on our distribution circuits and our head ends. So there's those 500 milliamp RCDs, 300, 100 with time delays built in. We've been doing this with generators for decades to give that sort of fault protection. We can do that with our sort of domestics and also our commercial installations too. Some people come to us and say that the split load boards are the devil and they can't be used, but they are still a perfectly good solution, heavily adopted by new house builders. And there is a UK specific regulation with these. They can still be used. You might have seen them before where they had two 63 amp, 30 milliamp RCDs in, and what you might see is manufacturers maybe changing them to 80 amps or 100 amp. And it's just asking that RCCD has no overload. So it's really looking at what's upstream of that. So either that will be the sort of cutout fuse, or if it's in a commercial environment, it might be the circuit breaker beforehand. So just considering those requirements when you're using split load boards. And it's actually really important here that the manufacturer's instructions are followed. We're not overloading those devices. We are using the devices in the set way, and we're keeping maybe those loads distributed across the 2 or 3 RCDs that are in that board. Another common one as well is we spoke a lot about TT today and RCDs, and especially in domestic scenarios, is that RCD means main switch is required. So we have a regulation on this, and it's a UK specific one. We talk about double reinforced insulation on those live incoming cables. So those cables from the meter will be insulated and sheathed, and that meets our double reinforced protection methods. Importantly, it's important that when we install these, that we keep those as short as possible, so no one can hang their coats on them or swing from them. We sort of clip those on the way. We use a proper tail gland. They're relatively inexpensive these days, that sort of grasps the cable. And importantly, we keep it insulated and sheathed all the way into the main switch. So we can still use that main switch, but we're making sure that any sort of earth faults is absolutely minimal. There may be times where you just want the 30 milliamp RCBOs on all outgoing ways, and that'll be fine. If you've got distribution circuits in there and you want that 1 second disconnection time, then you probably are now looking at changing that for a time delay coming out main switch. So it's just options really for you. But importantly, you don't need one. The requirement is sort of your 0.2 second disconnection or your 1 second disconnection times, but you may need to depending on how you design your installation. Good installation practice. Now, we sort of highlighted this earlier. So there's a fundamental difference between a type A and type AC and type B and type F devices. They are two different British standards. Importantly, the type A and the type AC have a tolerance to DC. They can't detect DC. They have a tolerance to it. The AC having a tolerance of none. The A having a tolerance of 6 milliamp. Well, it will still function. The type Bs and the type Fs will look at DC. They will be able to detect a DC presence of a form or magnitude, and when it gets to a certain threshold, they will be able to disconnect that device. That's the fundamental difference. However, importantly, type Bs and type Fs are lone rangers. They do not like to be near or downstream of As and ACs. They need to be on their own. And that's important, that also the way they operate, and they don't go blinding anything upstream. So if you've got installations that are predominantly domestic and you put a renewable sort of distribution board in there, maybe that's becoming a more common thing. If it's on a TT, you won't be able to put that downstream of a type A. You may have to go type sort of B or above for your main switch, or you might have to split the tails. So importantly, the way type Bs and type Fs works is completely different, but they like being their own ranges. And they have that higher threshold, sort of that 10 milliamp and above. And they also have that ability to disconnect if there is a DC fault present, unlike the A and the ACs, which will just tolerate it or may not even function at all. So it's important that we sort of split down. I'm not going to go into too much detail on this slide right now, because we talk about where RCDs and SPDs are in conjunction with each other, but importantly, it's a difference in what we call CT1 and CT2. We'll come on to this sort of later on, but it's about selecting. If you've got an RCD, you have to make sure you select the right SPD to avoid nuisance tripping. Can you risk assess these out, RCDs out? Absolutely, in commercial environments. So that's nowhere BA1, BA2, and BA3. So if you've got ordinary persons, so that's a domestic home, children, disabled persons, they all fall into ordinary sort of persons. No. Outdoors, no. In other locations, yes. Commercially, we can look at this, and it's a live risk assessment. That's important, and it's carried out with your clients. Your client needs to risk assess that, and you can help them with it. We have a great form you can download from the ECA, which goes through this. Typically, where you might see this is in sort of, for example, food processing plants where conveyor belts might be on commandos to switch them out very quickly for maintenance, or motors, or data centers. So every data center in the UK will have a couple of maybe 32 amp commando sockets for an A/B feed underneath the racks. They will not have 30 milliamp RCD protection. They will be in a controlled environment that's not accessible by ordinary persons. So absolutely, we still do this. It's not a departure, providing it falls into indent 2, and we append this to our electrical certificate, and the client's aware that it's a live risk assessment, i.e. if something changes in their business, they need to review this, not just shelve it. Testing, nice and simple with amendment 2. It sort of took away that sort of times value. So for times 5 value, sorry. So RCDs are deemed effective if they disconnect in less than 300 milliseconds at times 1. You can choose if that's at 0 or 180. The times 5 test isn't there anymore. You may wish to do it, but it's not essential. Just remember that the sort of old BS4293 RCDs are effective if they disconnect in less than 200 milliseconds. And for time delayed, it's anywhere between 130 and 500. We only need to test on the type AC setting because that setting is built into every RCD. RCDs, by their product standard, are always tested in the factory before we receive them. We just need to do that quick verification test. So it's nice and simple. ×1 on the AC setting of your test instrument, and you're looking at typically below 300 milliseconds. Again, that carries forward when we're periodic inspecting. So again, best practice guide 4 from Electrical Safety First is an excellent guide when you're doing EICRs. Again, we're just asking for that ×1. Other tests aren't mandatory, but may help you if you're fault finding. For example, I know a lot of people favour the ramp test if you're seeing something that looks a bit sensitive. Classification codes for these typically, and this again, this is a starting point. It's you as the inspector on site that makes the final decision. But typically, if there's an AC RCD that is functioning, typically we'd start at a code 3. So that's an older RCD that's not got any sort of evidence of being blinded by any DC leakage, and it's still functional upon test. You may recommend it's upgraded, but typically we're starting at C3 for us. So to summarise this, RCDs are extremely common in our electrical installations. They do much more than just protecting the user. Socket outlets, additional protection, fault and fire protection are also key benefits of these. We've had a quick tour over a lot of these today, but there are many RCDs. They do many different things. They have many different values, and they cost many different pounds. So we've got a whole abundance there in the last 5 years of different RCDs we select and getting them right. We can still risk assess them out in certain situations, and we've explained that today. And when you come to inspect and test these, again, it's dead simple. Could save on some periodic inspections time. That brings us halfway through. I decided it's going to be a long one today, but let's get through SPDs and lift busting. And in a way, it sort of these fall hand in hand with RCDs. But today we're going to talk a little introduction about SPDs. We're going to lightly touch on the regulations on this, nothing too onerous on that because they're a risk assessment. We're really going to how SPDs work and how they function. Good selection, because often that's done badly. And we're coming to a bit of a hot topic as well about verification, a little summary at the end. This is very kindly given to us by our friends at Merson, and we're going to talk briefly what sort of SPDs do. Now, everyone associates SPDs to the Lightning standard, and that's 62305. Although we help implement that in BS 7671, our wiring standard, what we do is all about the Type 2, the man-made. But I'll give you an overview of this all. Transient overvoltages are voltage surges that can reach tens of kilovolts in just a matter of microseconds. Now, with Lightning, we can get up to 200 kA of energy. That's in the worldwide standard. Fortunately, in the UK, we're not that lucky. Typically values of about 100 kA. So that's a lot less. And you might see Type 1 SPDs that have values of 25 kA. And you wonder, why is it 25 when Lightning's 100? Well, that Lightning being 100, when it hits the Lightning protection system, 50% of that's going to go into the atmosphere. 50% of that's going to travel down the conductor. 50% of that will go to Earth directly. The other 50% will end up in your electrical installation. And that's where that 25 kA comes from, a Type 1 SPD, which is traditionally a lot bigger. It's got a lot more energy to take, and we'll come on to that later on. Where we're interested in BS 7671 predominantly is Type 2s. It's the man-made switching. And that's typically an all indirect stroke. So Lightning sort of hitting elsewhere, and that transit coming into our networks. 20 kA, typically the values for those ones, most are sort of around the lower region of 5. You've got to remember that you see here there's a voltage spike here, and we'll come on to that in a moment, but it's a colossal amount of energy we're dealing with, and that may lead to premature aging of electronic components, equipment failure, and can cause disruption and financial loss. So what are the differences between the two? Again, Lightning protection 62305, and the reason we talk about this in our standard is where Lightning protection systems state that they need a Type 1 SPD. We need, as electrical contractors and designers, to put that into our systems. And that's why if you look through the book, we like to call it the piano keys. selection on there, but it tells us how to install those type 1s. So when it comes through installing devices for lightning protection, that's absolutely our remit. And we get a bit of that guidance from 62305, and that's dropped into our brown book, and that helps us select and erect the right type 1 SPD for that. And that's why we have mentions of type 1 protection zones 1 in our standard, because we need to implement that. But importantly, when you get a lightning strike, it gets to 90% of its energy within 10 microseconds. It's dead quick. And it takes 350 microseconds for that energy to deplete to 50%. It's a large amount of energy. When you come to indirect, so our lightning strikes or switching, it's a very, very small magnitude. It's up to sort of magnitude much quicker, 8 microseconds, and it's down to 50% within 20. Now, when we put these together, you can see the difference between a lightning strike, which is that large area of energy under the curve, and a switching transient. Switching transients are very short in duration and a very small amount of energies. And we can get this, from MCBs, contactors, motors going on and off, elevators, electrical accidents, switching banks, welders, air compressors, switchboard power supplies, all these sort of things can cause little sort of transients and switching. Where do we need them? Very simple. It's a risk assessment. So we're not going to dwell on this too much, but when you perform a risk assessment and that is required, then you'll install SPDs accordingly. It's important to get that right. Where a risk assessment says that you don't require these, then you won't. Installations now are looking for voltage or over voltage control, so they're looking at SPDs for that. But where it's risk assessed that they're not required, you've got a record of client's intention here. So if your client doesn't wish for SPDs, we've got an ECA model form where you can document that, and you can put it with your electrical certificate as well as evidence. We've spoken about risk, and if we do now say that risk does occur, so we need to implement things for that risk. We don't just stop at the AC circuits anymore. We also need to protect our DC circuits. And you might have seen sort of things like this, and this image is sort of courtesy of game. There is a difference between an AC SPD and a DC SPD. And if you ever sort of seen some YouTube videos on people sort of holding MC4 connectors together from solar panels, you'll see that huge arc from that direct current. And we've all been told about DC isolators, how they need to have a big clearance distance, and they have to open up rapidly to stop or extinguish that arc. It's the same for SPDs. If you fit an AC SPD in a DC circuit, you'll find if it does operate, it will often go on fire because it's that huge sustained arc. So risk does occur. If it does occur, we need to apply it to our AC circuits and our DC circuits too. In terms of things like solar PV and other sort of equipment, it may have it built in. So some inverters, for example, do have the equivalent built in. It's a conversation for you to have with the manufacturer. How do circuit protection devices work? Very, very easy. They literally just go conductive. They must always sit before the equipment they're protecting, otherwise they're useless. And the whole idea is that when an overvoltage occurs, they go of negligence impedance and conduct to ground. Very, very, very simple devices. As we spoke earlier on this presentation, type 1, class 1 are your sort of robust. They find they're much more expensive. They're much more robust in their construction because they got higher faults and higher voltage and currents that they need to put down to ground. So those type 1 devices are in LPZ1, so direct lightning strike. We're really looking at class 2 or type 2s. That's where most of our installation sort of sits. Type 3s is typically normally built into equipment. So predominantly we're looking at type 2s in our distribution boards. We're used to picking up circuit breakers and fuses off the shelves, and we can read these normally really, really well. Can we do it out of SPDs? Now, hopefully, this will give you the confidence to check that you've got the right SPD. They have markings on them, just like MCBs. What does all this mean? Here we've got a type 2, but it could easily be a type 1 or a type 2 or 3. So straight away in that corner that says T2, that's the type of SPD. So we need to check that we've got the right one. In this case, it's a T2, that means type 2. It could be a T1 plus T2 or many variants of. So it's important we get the right device, especially if you've been asked to install a type 1 SPD and you get given a type 2. It's not going to work very well in that situation. The next on there, we can see it says max 125 amp GL. That's its backup protection. And we try and go with the largest backup protection you can. So all that energy through that circuit breaker down the SPD. You don't really want the circuit breaker to destruct or to disconnect. A lot of these now, especially in domestic, you'll see they're rated at 125 or 100 amp. They can literally sit on the bus bar and they let the distributors use as backup protection. But be aware that when you're building larger panels or you've got larger installations, these might be 63, 32, or the largest frame size you can, and the manufacturer will state if it's fuses or electronic devices you can use. So that's really important. We talk about IMAX on here. If it was a type 1, it would be what we call IMP, and that's the maximum withstand it can take up 1. So if we had a 40 Ka incident, this SPD is done. It's done its job. It only has to do that once, and it will do it once alone, whether that be for lightning on a type 1 or it would be for indirects on a type 2. 40 K is the maximum impulse it can take out one time. UC, that's when these things start conducting. So if you think you're going to use an SPD for voltage control to get your voltages down in your grid, no, speak to your grid. Look at things maybe like voltage optimization or UPSs. That's the only thing that can condition your voltage. These will only start conducting at 275 volts and above. So we are looking at those big surges. IN, this is on a type 2 device, and that can take, a type 2 device can take around about a 20 Ka condition or fault around about 20 times. We say around about 20 times, that's what the product standard says, but there's no sort of ticker tape on this. It's not like got a little counting clock next to it. We don't know if that's had 12, 22, 18. We say around about 20. So it can take a little bit of impact quite often, up to about 20 times. Once these are done, they're done. They give you very, very small protection. That's what the UP stands for, 1.3 kV. So it will still work. It's in basically like the car limp home. It's just giving that a little bit of protection. The rest of the overvoltage is just going to keep going past it. And there may be some other writing from the manufacturer on these as well, maybe some normally open, normally closed contacts or some other additional information that may be useful. But it's important that when you pick these up from the wholesalers, you understand what it can do, what its capacity is. Here we brushed over this with RCDs, but there are a couple of variants of SPD, sort of common or differential mode, and why do they differ? Common mode is CT1, and what you'll see here predominantly this is for TN systems. Often it will say suitable for TNS or TN systems. This is because the neutral is actually connected to Earth with a metal oxide resistor, and there is a slight leakage through that. So with TT installations and RCDs, that would cause a tripping issue. It's the last thing you want on a Friday afternoon. On a CT2, which most devices are now by default, they will use a spark gap or a gas discharge tube between the neutral and PE. And that little gap there means that RCDs aren't going to trip. So to highlight the regulations of this again, your CT1s are for TN systems, CT2s can be used everywhere. Cable lengths. We talked very early on about making sure the SPDs are as near to the equipment as possible. I've seen these installed sort of 5 meters away from a distribution board. So they're not going to offer any protection at all. So we need to keep these lengths as short as possible. Conductor length of these is typically, we really want that down to the ½ meter. Some of them connect straight onto the bus bars now with a direct terminal straight onto the chassis. We don't want to go past the 1 meter. If we got, for example, CPC or earth lengths over that 1 meter, we can go onto the chassis. It's getting us down to earth as soon as possible. We want to keep that protection as good as we can to get rid of that over voltage. Verification. So how do you test an SPD? These are all tested in factory according to the product standard. In BS 7671, we only require a visual confirmation. So these typically will have flags inside them. So red light, green light, or depending on the manufacturer, it will say that the status window will change colour. That's all we need to do. It's really, really handy if we can wire these up to BMS panels. Some people wire these up to doorbell circuits. I think that's stopped now after several complaints, but you get the gist. If we wire these up to BMS systems, we'll see instantly when those SPDs go end of life, or they fail, or there's an episode. Importantly, you can send someone out to check, verify, and replace. There are testers on the market. Some are specialists, some are MFTs. For example, Metro as an MFT do this. Sonal and other manufacturers produce SPD testers. Typically, and I can't speak for all manufacturers how they work, they check the varistor element of SPDs. Some may vary, and they typically apply DC voltage at 1 milliamp. And they look at that when they're going to start conducting. We're looking at that conductor when they're going to start conducting. Ourselves and the rest of the industry, including Electrical Safety First, apply caution to this because we don't want to affect the RCD. Effectively, be the rod that broke the camel's back. So, as far as we're concerned, visual inspection is more than okay. So, in summary for SPDs, where your risk assessment states you should install these where required. Often, it's good to work with manufacturers with this because sometimes we over-engineer where SPDs are needed. And like I said, when you install one SPD, you might have to install several, especially if you've got multi-point distribution. And manufacturers can help you select the right SPDs in the right location, and you might actually be installing less than what you thought. So this is one of those occasions that you could really involve your manufacturer. Remember that DC circuits need protection too, so that might be built into the equipment, or you might have to look at separate DC SPDs for those. Making sure we keep our cable lengths as short as possible, and if you do have to fit retrofits, and this can be challenging SPDs, you might have to put sort of a remote indicator panel somewhere else on the panel so you can see if it's sort of gone end of life or if it's red light, green light. And again, it's just visual inspection only on these. We have gone through a lot of information today. We have lots of other information as well. It's all on our YouTube channel. So that's youtube.com/ECA Live. We've also got a lot of our Technical Tuesdays and a lot of our sort of heavy content on there as well. That's for members and also others who wish to look at that. For our members, we have a lot of information on our technical website. So eca.co.uk/technical. We spoke at the beginning about our BSI package. That's again, I think that starts at 5 users for £100 a year. That's really popular, especially with changes in standards at the moment. So 5839 part 1 and 5266 is being updated this year, and that's the emergency lighting standards, so that will hopefully be really useful. If you've not got it yet, you can log on and get the ECA app. So that's for you and your operatives. You can get all this information on that app and more. And we talked earlier about, we think we provide great support for our members. We've got our ECA helpline, which is available during normal business hours, 5 days a week, 9 till 5. Drop us an email or give us a call. A reward for all your hard work. I'm going to leave this on the screen. We'll come on to sort of Q&A in a moment, but I'll leave this on the screen for the duration. And I think we've got about 10 minutes left for any questions that you may have popped in the chat.
Well, thank you very much for that, Darren. Yes, we do have a few questions. Looks like mostly relating to RCDs and perhaps a couple for SPDs. Are you happy for me to just start from the start, or do you want to have a little look first?
I'll have a little look. I got one here from Eddie. Thank you, Eddie. No, it's really annoying me, by the way. But Eddie asked, my leg is getting better, and it's not. Should SPDs come as standard with an auxiliary contact? It's choice. The auxiliary contact is really, really, really useful. Again, it's sort of horses for courses, really. Yes, no one's going to look at in domestic. No one's going to look at SPDs while they're sat there under the cupboard. Commercially, they're of huge benefit. You might have liked the doorbell idea where people actually might wire this up to a little control panel, red light, green light, so they can see it next to the boards, for example. It's really a choice on that one. Not something we're looking to mandate, but I do like the option of the auxiliary contact there. We got one from Danny. Thank you for that, Danny. And I think it's really around about 62305 about why is there a requirement to bond an LPS in the event of lightning strike, high voltage transferred installation. Yes, that's in the 62305 standard. And really, it was looking at where you've got that risk. It's going to enter your building anyway, and it's about taking it into it basically in a controlled manner. And that's why certain light detection systems will require that bond to the MET of the installation. I know it sounds ludicrous, but often if that's not there, lightning will find its own way, and it could destroy other things. So everyone likes an easy ride, so does lightning. It's going to take the easy route. We want to give it that route, and we want that as safe as possible. And that route is normally get it down to ground, and we let it effectively, we invite it to enter our installation in a controlled way, in a controlled manner. And I believe that's why we do bond LPS systems. So from Danny, do we still have to fulfill the 130 to 500 millisecond disconnection time for selective RCDs? Now table 3A has been deleted. Yes, that's been written as that has been written in. So table 3A is still available from the ECA. We've kept that table. It's available for members. It's really, really useful. We've kept that. It's in our download section. If you've got an old copy of the regs book, you can go by that. Nothing's changed there. But what we've done now, we've written about the effectiveness of the RCDs, and we've talked about the 300 milliseconds, or for time delayed 130 to 500 milliseconds. So all we did is put that into written text, even though table 3A has been removed. We agree it was a useful table. We've still got it for our members to download. A great question from Christian. Are we saying we don't need additional protection for commercial cab socket outside supply? If that's a communications cabinet, so we're probably talking, so if that's communications cabinet, if it's inside an installation, then like the IT racks and stuff, you can risk assess that at. I'll catch up with Christine, I think, after to clarify his question on if he does mean, for example, if it's an external mobile communication cabinet or something like that, but I'll catch up with Kristen after that. Eddie's question, when RCD manufacturers state test regular, what is regular? Open-ended question on that one, Eddie. I think typically we're talking guidance about every 6 months. And the reason that was is because your clocks change every 6 months. It might be a great idea to test your RCDs, but some manufacturers may state monthly. Often, as we know, it normally comes on a 5-year periodic inspection when you go and press the button and nothing happens. But 6 monthly is the guidance on that. Some manufacturers do state monthly. Danny's got a really good question here about, does an RCD upstream of a bidirectional RCD supply a PV set on a TT system? So, for example, 100 milliamp type S supplied a dedicated board with bidirectional 30 milliamp also be required. So we're talking in a TT installation, Danny. I think you're right, and you've got a TT installation with an RCD main switch, and then you might have 30 milliamp RCD protection after that to your solar PV circuit. The simple answer to that is yes. However, most double pole RCDs or RCCBs are bidirectional. It's good to have a conversation with manufacturer there. Most of these issues sort of occurred around RCBOs and the way their electronic circuit is powered from the RCD. So it's not a get out of jail free card for any sort of double pole RCD. Both will be required to be bidirectional. You may find by default a lot of these double pole devices already are, and there's some guidance on there on electrical safety first. So again, if these devices are operating under test, then they'd attract typically no more than a C3 code. Thank you, Christian. Christian has said inside. Yes. So to clarify on Christian's great question there for commercial cab socket. So for IT cabinets and sort of bits like that, yeah. If you've got a TT supply, you still need to sort out your head end. You still need to sort out your fault protection. But your 30 milliamp bit, depending on how you install that cable, typically in armoured, could be lost with the risk assessment. Thank you, Christian, for clearing that one up. I think, Kat, we've answered them all. If we haven't,
one might have just popped in just in the end from Eddie. It says, SPDs, what do the DNOs think of us diverting faults down their earth path?
I'll be honest with that, Eddie. I don't know. Earth is Earth on that one. I really don't know on that one. I mean, to be honest, they do build surge arresters into their whole network anyway. It's not been something that, it's a great question. It's not been something that's ever been discussed or raised by the ENA or the DNOs, to be perfectly honest. They must be happy with the level of protection they're given on that LV HV feeder. I can only assume, but I can't speak for them. But to be honest, Eddie, we don't know. It's not something that's been raised, but we can ask.
And then just another quick one. Would an IT guy not be classed as an ordinary person?
Typically, then in that case, and our risk assessor is really good at this, is if you've got, they'd be skilled in IT, but not necessarily so skilled in electrical, but we've got to look at the risks there. So we're getting that circuit to that cabinet safely. So we're using ADS for that circuit to that commando outlet. Typically, the electrician will be plugging in the PDU inside that cabinet again, and the cabinet will all be bonded where it needs to be. Earthing's in place, ADS will happen. Typically, the IT sort of person servicing the cabinet will be the only person who has a key or a lock to that room or that cabinet. And importantly, they will be the ones plugging in. So we're looking at making sure the equipment is pack tested before use. The equipment goes through routine maintenance. So that might be checking the leads every so many years, for example. They're not necessarily playing with the fixed wiring at all. They're just plugging in to those PDUs and then making those final connections. We wouldn't expect someone to be walking off the street and doing that. Skilled electrically, no. Are they skilled in what they're doing? Yes. And we go through that in that risk assessment as a classic example of that. Certainly, if you had anyone who was plugging in equipment and they weren't checked or verified and you weren't happy with that, then you might introduce 30 milliamp RC protection on the PDUs. Some data centers do this, where it's co-located or shared location, where they don't have control of who's walking in and plugging equipment in and out. So on co-located equipment, they might drop that in.
Well, thank you. That's about all we've got time for. There's a couple of other things put through that I will send on to you, Darren. It might just be statements, but if there's anything Darren has to add, he can get back to you by email. But thank you everyone very much for joining. And this will be uploaded onto YouTube in the next couple of days. So look out for that and do share it with your colleagues. Okay, thank you.
Thanks, everyone.